let me first give you a brief history lesson to show you what led up to the development of a language WebAssembly. So, in the 90s, as mentioned before, 95, the Netscape browser decided HTML pages, they're boring. It would be very cool if we could offer some kind of programming language to enhance these HTML pages. And they asked one of their engineers, and he came up in a few days with ECMAScript. So ECMAScript was the first version of JavaScript. A little later, this ECMAScript was renamed to JavaScript because the language Java at the time was quite popular. At least this is what I've heard. And so they tried to surf on the wave of Java. I'm not sure if this is 100% true, but that's what I've heard. Now, JavaScript executes within a sandbox, even then. It's not simply executed directly on your machine, or well, it is of course executed directly on your machine, but it's sandbox. So errors, JavaScript code should remain very contained. And so the Netscape browser became very popular, offering JavaScript to its users. Now, JavaScript increased the popularity of Netscape, and other browsers quickly adopted JavaScript support, and JavaScript simply became the default scripting language for the web. It, however, was plagued with one big problem, and that was JavaScript was very slow. It could do simple stuff for your website. It could improve the usability of your website, but it couldn't do very many complex computations very quickly. Now, a language is not inherently slow. Here's some JavaScript code. You can't state about a programming language, this language is slow or fast. That doesn't make much sense. It's the way you execute this program which makes it slow or fast. So if we think about what executes JavaScript, well, initially, JavaScript was being interpreted. So you write a program, for example, a program that reads this line var a is 0, and then goes, for example, an interpreter would go through a big branch. Okay, it says a var instruction, let's reserve some memory, let's store the 0 value, and you could write a C program that basically parses this and then has a lot of if-else branches or case switches, depending on what instruction you read, what you have to do. And you interpret this line by line. That's initially how JavaScript was executed. Now, what's an alternative to interpreting? That's compilation. Why not translate JavaScript immediately to machine code? Now, there's a big reason why, and that's machine code is a lot harder to reason about, and so you need a way to keep the machine code in this sandbox. So it is interpreted. When you write an interpreter and your interpreter doesn't contain any vulnerabilities, then you should feel relatively safe. You're never safe, but you should feel relatively safe. However, once you get to machine code level, stuff just becomes a lot more complex to reason about. But the consequence is this is slow. So at a certain point, people decided, let's create just-in-time compilers. And what's a just-in-time compiler? What does that do? Well, let's say you have this same piece of code here. This compiler, this just-in-time compiler, notices, oh, we have a loop, or we have a certain piece of code that is executed a lot of times. Let's translate this piece of code to machine code and execute it directly as machine code. Now, this is a lot faster. So just-in-time compilation of JavaScript improved the performance immensely. Only you run into new problems. Again, this code, this machine code, it needs to be sandboxed. And sandboxing machine code could be considered a much more difficult job than sandboxing regular source JavaScript. And there's another thing. Now you're including a compiler. First you had an interpreter, now you have a compiler. Compiler is a much more complex program. And this compiler program, it can contain mistakes. Your translation might be wrong. You might be able, actually, let's say it in this way. When you translate a program from one language to another, how are you guaranteeing that those two programs are correct translations? There's formal ways of looking at this. This is research being done within our research group. But in general, it's extremely difficult to guarantee that your machine code representation of your program is actually the same as your source code. So your compiled program might suddenly do something different. So that's another vulnerability added here, or possible vulnerability. So this is considered to be more dangerous. But they did succeed. The JIT compilers are everywhere today, so this does happen. And it's possible to sandbox machine code. At least developers are currently convinced that it's secure enough to do this. You can never really say secure, but secure enough to do it in practice. And from this development, you could say, the fact that we were now not running JavaScript anymore as a programming language of the web. No, now we're actually running machine code. Okay, machine code compiled from JavaScript, but it's still just machine code. And you're running machine code and you're sandboxing machine code. So, if you're already doing that, why not allow us to run machine code compiled from C or machine code compiled from any other source language in this sandbox? This offers us performance and we already have to sandbox this code, so why not? And that's exactly what Google did. They came up with a native client. Google Native Client, or NACL, was used. And suddenly you could run in Google Chrome arbitrary x86 code inside of a sandbox. And a website could use this to enhance performance. They could now run machine code, so you could visit the website and this website could actually execute x86 code directly on your machine within a sandbox for security. And this, of course, is a lot faster than what we did before. Machine code is the language of your processor. You shouldn't be able to go much faster than that. So you might wonder, well, aren't we done? This was a good solution. Well, I'd say yes, it was a good solution, but no, we're not done. First of all, x86 is just one assembly language or one instruction set architecture. Native client needs to work, in theory, browsers needs to work on any machine. And this can be your phone, and this can be from an AMD processor. Well, could have the x86 instruction set architecture as well, but you have many different instructions architectures on which this needs to run. So this was a problem. So then they developed portable native client, which ran on multiple architectures. And then a different problem. This just worked for Google Chrome. And then you could convince other vendors to also implement this, but that's not what happened. Since we were now running arbitrary machine code in web browsers, and web browsers were responsible to isolate this code, the different software vendors decided to come together and start from a clean sheet. There's probably no need to support every possible machine instruction of every possible architecture on the web. What they wanted is a machine language that is both fast, high performance, but also easy to secure, easy to sandbox. And so the creators of Chrome, so Google, Microsoft, Mozilla, Apple, they all came together, and together they started working on a new language for the web. Something to finally replace JavaScript. Well, no, not replace. Something to work in tandem with JavaScript for high performance applications. And what they came up with is WebAssembly.